So thank you for your patience.
Okay, take care.
As we're getting started, what a good crowd tonight. We underestimated the demand for seats for this particular performance. Sorry about that. We do have an overflow room, but you're here and they're there, and hopefully everything will work out just fine. I want to introduce myself. I'm Don Farish, president here at Roger Williams University, and this is the last for this year of the President's speaker series. And tonight we are blessed to have the presence of Dr. Naomi Oreskes from Harvard University. And just briefly, Dr. Oreskes actually began her undergraduate degree at Brown and then ended up finishing her undergraduate degree at Imperial College in London, worked as a geologist for a few years and went back and received her PhD at Stanford, and has moved around a little bit. She's been at campuses such as Dartmouth and NYU, but has spent much of her career at the University of California, San Diego, and then fairly recently has moved to Harvard University, which is obviously more convenient since if she's going to drive home tonight, San Diego would be a long haul. So, so we waited for her to get to the East Coast, and then it all worked out quite nicely. Dr. Oreskes has arrived at her discipline at a very interesting time, and her particular specialty in the history of science is really focusing on the question of how it is that science findings and discoveries get factored into the broader community for purposes of being incorporated as part of our general understanding of how the world works. And we know from our own personal experience that this is a very difficult task to accomplish. To this day, there's a sizable fraction of the American public that has not accepted the idea of evolution by natural selection. We know currently in the American presidential campaign, bitter divisions on the issue of climate change, even whether it's happening, let alone whether it's induced by humans. And there's something about this that from the science perspective is deeply disturbing, because the way science operates is that we believe that we are arriving at something that approaches truth, or at least a generally broadly held conception of how to interpret the results that we see around us. And the failure of the broader society to accept that information is frustrating to scientists, speaking as one. But on the other hand, perhaps it's because science just does a lousy job of persuading people about the validity of its work. Dr. Oreskes wrote a book a few years ago, The Merchants of Doubt, that was subsequently made into a film in 2015, and has been a sought-after speaker and writer on the issues of science and how they factor into the findings of science factor into our human understanding for a number of years. So we're very pleased to have her with us tonight, and I ask you to join with me in giving a warm welcome to Dr. Naomi Oreskes.
Much. It's really a pleasure to be here tonight in Rhode Island and to have this standing room only crowd and to be in this beautiful room. I don't know why the law schools always get the best rooms, but they seem to. So I'm a historian of science. I study the development of scientific knowledge, but tonight I'm going to talk primarily to us as citizens, as people in the world who have to grapple and deal with scientific questions. And I just want to say, I've been teaching for 30 years, and I know that staring at someone standing behind a podium is not the best thing in the world, but unfortunately the clicker doesn't work, so someone may come in the middle of the talk and give me a clicker, and if they do, I'll stick it in and then I'll start walking around. Otherwise, I'm afraid I'm a little bit stuck here by the podium, so thank you for your understanding. So as citizens, we face issues every day that implicate us in scientific claims. It's not just scientists who have to grapple with scientific information, it's all of us as well. Should we vaccinate our children? Should we accept genetically modified crops? Should we be doing something about climate change? And often the science around these issues seems rather uncertain. And this, it turns out, is not a coincidence. Scientists work at the boundary between the known and the unknown. That's what science is all about. It's a process of discovery. So it means by definition that at the research frontier, at the edge of research and discovery, there's always uncertainty. And sometimes to some people, that uncertainty can seem like grounds for rejecting the science. In my own work on the history of climate science, I showed that by the early 1990s, there was an extensive literature affirming the reality of the human fingerprint in the climate system. That is to say that the climate was changing and the main driver of that were human activities. But this led some people to ask me, well, so what? Even if scientists do have a consensus, why should we trust them? And I think that's actually a legitimate question. A lot of scientists get kind of nervous when people say things like that, but I think it's legitimate as citizens for us to say, well, what is the basis for us believing that these claims are true? To accept the reality of climate change or the safety of vaccinations, we have to trust science. We have to believe in the claims of scientists. Now, a lot of scientists don't like talking about belief because it sounds like we're talking about faith. We believe in God, we believe in religion, but we don't believe in science. And indeed, whenever one thinks about the question of belief in science, it raises or brings up the history of Pascal, one of the greatest mathematicians in the history of science. Pascal is famous for a number of things, but among them, something that has come to be known as Pascal's wager. Okay, here's a possibility of a clicker so we can take bets on whether this will work. So, let me give this man a message. I'll talk about Pascal while he messes with the AV. So Pascal asked a very important question. The question was, should I believe in God? And Pascal reasoned the following way. He said, look, if I believe in God, but she doesn't exist, well, actually, he didn't say she, but if I believe in God and she doesn't exist, there's not really much lost in that, except maybe I waste a few hours in church on Sunday. But if God does exist and I don't believe in God, then I'm going to, fantastic, thank you so much, then I'm going to burn in hell for eternity. And so Pascal said, I'm much better off believing in God than not. Or as one of my professors in college put it, he clutched for that handrail of faith. Now, many of us do clutch for the handrail of faith in many different ways of life, but science is not supposed to be a leap of faith. But is it, maybe? I would argue that actually for most of us it is. That most of us actually have no idea how to judge whether or not scientific claims are true. And so actually, most of us take that leap of faith. We vaccinate our children, and we accept that evolution may well be true. And like Pascal, we hope that the risks of accepting science are less than the risks of rejecting it. Now, if you asked philosophers, say 100 years ago, why we should believe in science, or even if you ask scientists today, many people would tell you, well, the reason we believe in science is because scientists use a particular method that guarantees the accuracy of the results. And that method, in theory, is supposed to be what we call the scientific method. Now, what do we mean by that? Well, any of you who have taken a science class, probably somewhere along the line, got presented something like this. Scientists develop hypotheses, they deduce the consequences of those hypotheses, and then they go out into the world and make observations or do experiments to test whether or not those consequences are true. And if they are, then scientists say things are good, full steam ahead. Now, in the history of science, we certainly can find some examples of scientists using the scientific method. So a famous example involves the test of the theory of relativity. When Albert Einstein first developed the theory of relativity, one of the startling predictions of that theory was that space-time, the fabric of space, could be bent in the presence of massive bodies. That was not something that anyone would have thought before, and people said, well, if that's true, then light doesn't travel on straight line paths, it actually gets bent along the bending of space-time, and it would be bent in the presence of a massive body. So any light that travels close to a very massive body, like our sun, would actually be bent along the fabric of space-time. And so scientists in the 1910s said, well, we could test that hypothesis. The next time there's a solar eclipse, I don't know if I have, does this have a laser pointer associated with it? Hold on, maybe that? Yes, good, okay. The next time there's a solar eclipse, we could actually look at some starlight from a star that's on a path very close to the sun. Normally we wouldn't be able to see it because it'd be too close to the sun, but with an eclipse we could. And we could see whether that path of light is actually bent by the bending of space-time. This test was performed in 1918 by Sir Arthur Eddington, and indeed, he found that light was bent in the presence of massive bodies. And this was taken as proof of the accuracy of the theory of relativity, and it was written up in newspapers around the world, including in this article from the Times of London. Now, philosophers sometimes like to call this deductive nomological model, because academics always like to come up with complicated terms for simple things, but also because the idea here is that the deductions we make shouldn't just be deductions from hypotheses, but in the ideal cases, they're deductions from laws. Nomological means having to do with laws. And we want them to be laws because if science is going to be powerful, then ideally our claims don't just apply in certain places at certain times or for certain people, but they're laws. They apply for everything under all conditions at all times. So we would take a law of nature, deduce its consequences, and then observe the consequences. And there are many famous examples in the history of science of laws. One that almost everybody has seen is E equals mc squared. But it turns out there are a number of problems with this model of science. And one of the problems is something that philosophers call the fallacy of affirming the consequent. And what that simply means is that a false theory can make a true prediction. So just because the prediction of a theory comes true does not actually prove that the theory is correct. And the most famous example of this comes from the history of astronomy. When Copernicus first proposed the idea that the Earth was not the center of the universe, but that actually the Earth moved around the sun, people said, well, we could test that prediction. Oh, I should just back up and say, when Copernicus first proposed his idea, the existing theory, the Ptolemaic theory, that held that the Earth was the center of the universe, actually made extremely accurate predictions of things like solar eclipses and the movement of the stars. So people said, well, why do we need a new theory? We have a theory that makes accurate predictions. Today, we would say that that Ptolemaic theory was wrong, and yet it made very accurate predictions of many things. So just because a theory makes an accurate prediction does not prove that the theory is correct. And that's called the fallacy of affirming the consequent. But there's also a second problem, and it's the problem of auxiliary hypotheses. And that simply means other hypotheses that we may be implicitly testing at the same time, but not necessarily realizing. So, if we turn to Copernicus, people said, well, look, if the Earth is moving, as Copernicus says, we should be able to detect the effects of that motion. And there was a big, big debate in the late 16th and early 17th century about this question of whether or not there were detectable effects. And one of the detectable effects that astronomers deduced from the theory was that if the Earth is moving, there ought to be a change in the apparent position of stars as the Earth moves through its orbit. And that's known as stellar parallax. So imagine this is December. I'm looking at a star, a bright, distinctive star like Polaris or Sirius. And in December, I see that star against a backdrop of a certain set of stars in the sky. But now the Earth moves from December to June. And come June, I'm looking at that star from a very different angle. Now I see that star against this backdrop, and it's quite different. So it's as if I were looking at that nice woman in the purplish shirt in the middle of the room with a nice chain, and here I look at her and I see behind her a man, a very nice young man with a baseball cap, but if I walk over here and I look at that same woman from a different perspective, now I see her against the backdrop of a man in a blue and sweatshirt with stripes, right? Okay, so that's stellar parallax. And that angular difference, this angle between what I'm seeing here versus what I'm seeing there, is called the stellar parallax. And people said, well, look, if the Earth is moving, we should see that parallax. So they looked, and they didn't find anything. So the test failed, and many people argued that therefore the Copernican theory could not be correct. Now, in hindsight, we know what went wrong. In hindsight, we could say that the problem was that there was an auxiliary hypothesis at work here. That is to say, an assumption that people were making that turned out not to be true. And what was that assumption? The assumption was that the Earth's orbit was large relative to the distance to the stars, and therefore that the stellar parallax would be large. So today we would say that the reality is something more like this, that the Earth's orbit is actually very small compared to the distance to the star, and therefore this angle is very, very small as well and hard to detect. But it took a long time for scientists to sort that out. In fact, it wasn't until the 19th century, so more than 200 years later, that telescopes became strong enough, sensitive enough, to detect the stellar parallax. So we can say in hindsight that actually there were two auxiliary hypotheses at stake here, the second one being the assumption that the instruments that they had were sensitive enough to detect the effect. So these are two examples of why the hypothetical deductive model doesn't really work to account for the success of science. Now, there's another problem as well, and that's simply that a great deal of science doesn't even fit the model of what we think the scientific method is. So it turns out that a tremendous amount of science doesn't fit the scientific method at all. So we call it the scientific method, but it's not what actually many scientists do. And there are many, many examples of this in the history of science, but the most famous one is this man, Charles Darwin. When Darwin went on the voyage of the Beagle with Captain Fitzroy and sailed to the Galapagos in South America, he wasn't testing a theory. He wasn't testing a hypothesis. He wasn't testing a law of nature. In fact, he really didn't have any hypotheses. What he knew was that he wanted a career as a naturalist, and he knew that he was never going to be a doctor. He had originally started studying medicine. He hated the sight of blood, and he knew he had to earn a living some other way. And he thought that if he went out on the voyage of the Beagle and made observations, that he could make a contribution to science, but he wasn't testing any theory. And he collected a lot of data, a lot of information, including the famous finches that we've all heard about. But actually, Darwin had no idea what the significance of these finches were. He threw them in a bag, he took them back to London, and it was only several years later when he began to think about this idea of natural selection that he actually went to an ornithologist friend to help him identify these finches, and then came up with the idea that they were somehow reflective of natural selection. So this way of operating, of collecting data first, of making observation, and then developing theories out of the data, is referred to as the inductive method. And a tremendous amount of science is inductive. So it's not to say that it's good or bad, it's just to say that it's different from the standard model, and that scientists do a lot of different things, including some very good and famous scientists. But scientists also do modeling. Modeling basically amounts to the idea of sometimes you see things in nature that are hard to understand. They're hard to explain. And as a scientist, you want to be able to explain the things you see in the natural world. In the 19th century, the late 19th century, one of the things that geologists saw that they wanted to explain were folded rocks. So in many places in the world, from the Appalachians to the Alps to the Highlands of Scotland, geologists saw there were many places in the world where rocks were folded into big, big, big folds, sometimes hundreds of kilometers across. Now, we all know that rocks are extremely hard, so how is it possible to take hard rocks and fold them as if they were putty? And not only that, sometimes these folds were so big that they were actually turned over on their side. This is called a recumbent fold. So here's a layer of rock, and it's folded all the way over so that the same horizon reappears beneath it, in some cases many kilometers below. And often these recumbent folds also had faults through them. So there were faults in which the rocks were displaced along these dipping layers. And so the question was, how are these folds created? And why are they faulted? And how are rocks that are so hard folded as if they were putty? And so scientists built models. So this is Henry Cadell, a late 19th century geologist. You can tell he's a geologist because he's wearing Wellington boots. And what he argued was that, well, you could explain these features if some kind of force compressed the rocks from the side. And so he built this model with a piston and clay and mud and sand in order to prove, or at least to demonstrate, the plausibility of this hypothesis, to say that you could get these folds if rocks were going to be compressed. And this later became a major source of a kind of line of argument in the debates over continental drift and plate tectonic theory in the 20th century, that it was possible to produce these features in this way. Now, nowadays, scientists don't generally make their models out of clay and pistons and wood wearing Wellington boots. They mainly make their models using computers. Computer models are what are sometimes called numerical simulations. In contemporary science, computer models are extremely important because it's a mechanism that scientists have for testing theories. And computer models have been particularly important in climate science. Why do I say that? Well, one of the biggest questions in climate science is what scientists call climate change attribution. That simply means We know that the Earth is warming up. We have instrumental temperature records that show us that the Earth has warmed about 1 degree C since the Industrial Revolution. So these are measurements. It's observed. This black line are the observed measurements. So it's not a theory. It's not a hypothesis. These are measurements. But how do we know for sure what's driving that climate change, that warming? Well, you can build a computer model in which you try to simulate, to reproduce the observed temperature record using different forces that you know can affect the climate. So this is a model result that shows the effects of various different, what scientists call forcing functions, that is to say causes of climate change. So sulfate aerosols, we see mostly cool the climate. Volcanic eruptions can either heat or cool the climate, but overall have not much net effect. Ozone can slightly heat the climate, but not a lot. Solar radiation varies a lot. It goes up and down. But here's the only thing that really causes the atmosphere to warm. It's the increase in greenhouse gases. So this is the known increase in greenhouse gases here, and the amount of temperature change that physics tells us you would get from that amount of greenhouse gases. And what we see in the model result is that in order to match the observation, the correct answer is all of the above. That is to say, all of these different factors affect the climate, the sun, volcanoes, sulfate pollution, ozone, but the only thing that drives the warming is the greenhouse gas component. Now, this observation, that scientists do a lot of different things, use a diversity of method, led the philosopher Paul Feyerabend famously to say that in science, anything goes. That is to say, he's often quoted as saying anything goes, but the full quotation is actually this: the only principle that does not inhibit progress is anything goes. And what he meant by that is that science is a creative activity. Scientists try a lot of different things in order to understand the natural world. Sometimes they follow the deductive nomological model. Sometimes they do inductive work. Sometimes they build physical models. Sometimes they build computer simulations. And all of this is part of a diverse and creative activity to try to help us understand the complicated and beautiful world that we live in. But that leads us to a problem. If there isn't a scientific method, if scientists do a lot of different things, then what is the basis for believing that the results of scientific investigations are correct? And the short answer to that question is evidence. We're in a law school here, so this is something that I've written about the parallels. We often think of science and law as being very, very different kinds of activities, but actually they have one really important thing in common, which is that arguments have to be based on evidence. You can't just say, this is what I think, and therefore you should believe it too. You can't just say, I'm telling you to believe me. You have to have evidence. So I've just given you evidence about the history of science. I've given you examples of things, so historians also need evidence. But that leads to the question, and I have a whole different lecture that I'll give maybe a different time if you invite me back about what constitutes scientific evidence, right? We can ask that question, well, how do we decide what constitutes evidence? But the short version is evidence is pretty much whatever scientists say it is. And they judge it and they evaluate it. And if they're lucky, if things seem to be lining up, they come to consensus. And by that we mean that scientists, if they have enough evidence and they believe the evidence is strong enough, may come to a point which, as a community, they begin to say, yes, we know this is true. Yes, we have tremendous amounts of evidence to support the idea that Darwin first proposed more than 150 years ago, that species change over time, and that the driving force of much of that change is natural selection. And yes, we have evidence that our climate has changed, and the driving force of much of that change is greenhouse gases in the atmosphere. Now, the idea that science is essentially a consensus of experts judging evidence upsets a lot of people, because it sounds like an appeal to authority. It sounds like we're just saying, well, you have to trust scientists because they're the experts. And of course, many of us were taught in school that the appeal to authority is a logical fallacy, that you shouldn't believe something just because an expert says it. Well, I want to make the somewhat controversial claim that actually science is an appeal to authority, but it's not the appeal to authority of individuals, it's the appeal to authority of a process. That is to say, we're not appealing to the authority of an individual, no matter how smart that individual is. So we don't believe that E equals mc squared because Einstein said it. We believe it because his colleagues and an entire community of scientists tested it and came to the conclusion that it was correct. Another way of thinking about it is that scientific communities are like juries, but they're juries of scientific peers. So if you look at this photograph, what you see here is here's a woman, a scientist, and she's showing evidence to her colleagues, right? She's got some kind of graphs or charts or photographs here, and she's showing it to her colleagues. Now, I have to say, I'm a little suspicious that these people are actually scientists because they look too happy. They're also shockingly diverse. But, you know, we'll give them the benefit of the doubt that these are diverse, happy scientists. And that's good, too, because diversity is good epistemologically. I'll say more about that in a minute. But the bottom line is this. Scientific knowledge is the intellectual and social consensus of affiliated experts based on the weight of available evidence and evaluated according to diverse but time-tested methodologies. So there isn't one method. There are many methods, but those methods have stood the test of time. So I've made an analogy that, sometimes surprises people. We often talk about science and technology as very different things, but actually I think the reason for our belief in science is actually rather similar to the success of technology. So if you think about the modern car is an incredibly reliable device. Most of us get up in the morning and we go to school or go to work and we put the key in the ignition and our cars start. And we aren't surprised by that. Well, I had a car in college where I was surprised every time it started, but you know what I mean. We take it for granted that our cars work, but why do they work? They don't work because of the genius of Henry Ford or Daimler or Benz. They work because the modern car is the accumulated result of the expertise and experience of thousands of automotive engineers who have worked on cars over the past 100 years. And of course, in this example, I show you a plug-in hybrid because you should all now be, well, you should keep driving the car you're driving. Some of us talked about this earlier, but when the time comes to buy your next car, it should be an electric car. So, why should we believe in science? Because our scientific knowledge is based on the accumulated experience and expertise, not of one genius like Darwin or Einstein or even Copernicus, but because of many people working together over a long course of history. Science works like our cars because of accumulated expertise and experience. So we should believe in science as a process because by and large, like our cars, it works. But this leads us to one more thought. Why should we believe in science? Well, or why should we believe in climate science, I should say? Well, because if we don't and we're wrong, the consequences, as in Pascal's wager, are pretty darn dire. But if we do believe in climate science and it turns out to be a big hoax, well, then we will have created a better world for nothing. Thank you very much.
We have opportunities for questions. I cannot be in two places at once. So what I'm going to do is take questions on this side of the auditorium. Those people who do have questions can come to the front and line up for questions by the microphone right there. I ask that you try to keep your questions brief, giving us opportunities to have more questions asked. Who would like to be the first person to ask a question? And the only thing I'd like is that the first two questions come from students.
Come on.
All the people lining up on that side. I'm just going to focus on this half. Who wants to ask a question?
Okay, we have someone.
There we go. We got. Thank you.
Hi. Thank you so much for your talk. It was wonderful. So I'm a biochemistry major, and I just wondered if you have any suggestions for communicating with the general public when you're communicating with family, friends, and peers that are not in your major for conveying your interests and your passions and just general science.
That's a great question. Well, I think what you just said is really the answer. It's about your interest and your passion. It's about explaining to people why science is interesting, why you're passionate, and what you get out of it. What do you learn when you study science? You know, do you feel a sense of appreciation of the natural world? Do you feel empowered because you understand things you didn't understand before? Do you feel motivated that you could actually solve some problems if you know the science behind them? So I think, you know, there are many different ways you can explain to your friends and relatives why you care about science, and the most effective thing you can do is tell your own story.
Thank you.
More questions?
That was a great talk, by the way. Thank you.
Thank you.
So I know the climate issue is really big right now. It's eclipsing a lot of other issues. Do you have any other scientific debates on mind that might be eclipsed by the climate issue today?
You mean other things that I think are important that we're neglecting?
Absolutely.
That's a really good question. Well, you know, it's interesting. When I first started reading about climate science, I was slightly skeptical myself in the following way. I had heard about climate change. You know, I knew some scientists were worried about it. But my own inclination, based on what I knew, was to think that biodiversity loss, habitat loss, that those were more urgent questions. But as I started to study climate science, I became more concerned about climate change because I see it as a kind of overarching issue that, you know, we could preserve habitat. So like we could preserve coral reef habitat by preventing overfishing, let's say. But if the oceans warm 2 or 3 degrees, those corals are all going to die anyway. So they're not really either or issues. Overfishing and, you know, damage to reefs from other things are also important. But the climate issue is one of these things that if we don't fix that, a lot of our other efforts in other areas will end up being in vain. So it's hard for me not to feel that climate change is very, very central. That said, certainly there are many important issues in the world, right? And I certainly would never want to say that, you know, your issue doesn't count because it's not as important in climate change. And of course, so many of these things are interrelated. So I guess, you know, one of the things that many people would say is a hugely pressing issue in the world today is inequality and poverty, right? And I agree with that. But again, these things are linked. So if you've read the Papal encyclical on climate change and inequality, one of the things that I think is so brilliant about what Pope Francis did is to show how these things are interconnected. And they're interconnected in part because if climate change continues unabated, it will be the poor who suffer most of all for a variety of reasons, some of which are obvious, some less so. It's also a matter of justice. We in the rich, wealthy countries of the world, the United States, Europe, Japan, Canada, Australia, we have created most of the fossil fuels that are in the atmosphere today. We have benefited from using fossil fuels, but many of the impacts of climate change will hit in countries that did not benefit from using fossil fuels, like Pacific Island nations, Bangladesh, poor countries around the globe. So again, they're interrelated. So you can certainly work on inequality and poverty from the perspective of poverty amelioration, but I think those of us who care about the climate issue as our primary thing, and those of us who care about inequality and poverty as our private thing, the Pope has really given us a kind of blueprint for thinking about how we can work together so that our efforts are reinforcing and sustaining, and that we see this as a both-and project rather than an either-or project.
More questions?
You have one here?
Well, I have read your book, and I'm really amazed at the number of references that you have at the end of the book.
I'm an academic.
One of the points that you make in your book that I think you didn't get across to the audience is that there are organizations that examine evidence and then they debate it and so forth, and then they make their final judgment. And there are many different kinds, and we've had some on climate change, and they've made, you know, deeper and deeper serious comments about what effects are taking place. So let's not overlook the fact that we're not just looking at one or two opinions. Many times we're looking at a multiple of opinions when people make statements.
Yeah, absolutely. Well, thank you for making that point. Maybe I can bring my slideshow back up and go, if I can, see if I can do this. Is there some way to go back to the beginning? So just give me 1 second. I'll see if I can pull it up. There we go. So thank you for that. Right. So obviously this is only a small part of the work I've done on the history of climate change, climate science, and the history of science in general. So in the book Merchants of Doubt, my colleague Eric Conway and I really looked at the question of people who are trying to undermine our belief in our faith or our trust in science, and why they would do that. And so Merchants of Doubt really tells a very disturbing story about people who, for political and economic and ideological reasons, deliberately, consciously work to undermine our confidence in the results of scientific investigations. So it's kind of a disturbing book, it's kind of a downer, and I decided tonight to talk about something a little bit less depressing. But one of the points that we did make in the book, and that also I've talked about in some of my other talks, gets back to this question of scientific consensus. So, and it gets back to this question of the appeal to the authority. When we talk about scientific work, we're not just talking about an individual scientist or 2 or 3 scientists. We're really talking about communities of people who are working together on complex and in some cases vexing issues. And this is one way in which science has really changed since the days of Copernicus. I mean, even Copernicus himself didn't work alone. He was part of a community of astronomers working in Bologna in the late 15th and early century. Kepler was corresponding with Galileo. These people even then were part of communities of investigators who worked together, or sometimes against each other, but who were sharing data, who were communicating, because that collective appraisal of data has been a really important feature of science for a long time. But it's become even more important in the modern world, where we now have very large communities of scientists who organize themselves into groups who take on the task of trying to say what the consensus of scientific expertise is. And so when I wrote my 2004 paper on the scientific consensus, I started this work initially by reviewing the reports that had been written by major scientific organizations and societies. So that included groups like the National Academy of Sciences, the most prestigious organization of distinguished scientists in America, the National Research Council, the Royal Society in the United Kingdom, the Intergovernmental Panel on Climate Change. And what I found was that all of these groups had written reports in which they said, yes, there's climate change, yes, it's happening, yes, we can measure it, and yes, it's mostly caused by human activities, greenhouse gas emissions and deforestation and land use changes. And I thought that was very important because these organizations, in a sense, represent the pinnacle of scientific expertise and experience. And what they had done in writing these reports was to express what they believed was the consensus of scientific expertise. But I was also interested in another question, which was the following. We know that leadership doesn't always represent the views of the people who they are supposedly leading, and we certainly know that in politics that's a big problem. It can also be a problem in religion. I mean, the Pope this present Pope is changing a lot of things, but the Pope may say that birth control is not acceptable, but we know that most American Catholics do in fact use birth control, right? So there can be a gap between what leaders of organizations say and what the people in those organizations are actually doing. And so I wanted to make sure that what the leadership was saying about the science was consistent with what ordinary scientists, what I would call rank and file scientists, had to say about climate change. And so I did a study, and it was a study that at the time seemed like a kind of obvious thing to me to do, although now people say I invented this technique. I don't know if that's true, but I'm credited with inventing the technique of consensus analysis, which is simply to say, let's look at the peer-reviewed scientific literature. Let's look at the papers published by working scientists in their laboratories, out in the field, see what's in the peer-reviewed journals, because that's where the rubber hits the road. That's, if you pass the test of peer review and get your claims published in the literature, then that counts as a scientific knowledge claim. And so I simply posed the question, if I take a random sample of the peer-reviewed literature, how many of these papers disagree with what the scientific leadership was saying at the time? And the shocking answer that I found was none. There wasn't a single paper in this sample that I took that disagreed with that basic claim that climate change was underway and mostly caused by greenhouse gases. And so I published that because I thought that was an important result, because it showed that there really was this consensus, that there really wasn't an argument in the scientific community. And when I published that result, I started getting attacked. We talked about this with some of the students today, and I started getting attacked by people who said that there wasn't a consensus and that there was a big fight going on. And so then I became interested in, well, who are these people who are saying that? Because my data is pretty clear, and I'm pretty sure that I did this study right, and I'm pretty sure I'm a pretty well-trained historian, and I have a PhD in geology and history of science, so I'm pretty good at reading scientific literature. And it was that question of who was trying to undermine this work, who was trying to persuade us that there wasn't a consensus. That was the question that led to this whole story of climate change denial, which became the book and the film Merchants of Doubt.
More questions? Right here.
So I know like kind of firsthand how difficult it is to get people really like interested in science and get them like kind of going with a lot of that. Do you have any advice to any of us who are interested in pursuing a scientific career and also possibly teaching others and how to get others inspired and really get going and want them to learn more about whatever they're interested in the sciencey field?
Mm-hmm. Well, I think that if you are interested in science, you absolutely should pursue it, and you should feel empowered to know that you're in a field that has a great and long history, and that there's a long history of scientific investigations helping us understand the world we live in, making the world a better place, helping us to solve real problems. And one of the things that I think is good about the story we told in Merchants of Doubt is that, I mean, the story is a story of sort of what we call serial contrarianism, that what we showed is that it's not just climate change where we've had to face this issue, but a whole set of other issues as well, including acid rain and the ozone hole. But the good news is that we actually solved these other problems on the basis of good scientific information clearly communicated by scientists. And especially if you think about the ozone hole. I went back and reread our chapter on ozone the other day, and I thought, you know, these guys did something unbelievably great. They recognized a problem that no one else not only did recognize, but could have. I mean, think about it. If scientists hadn't realized there was an ozone hole, we would be here today, and we wouldn't be able to go outside for more than 20 minutes without getting serious sunburns. And the rates of skin cancer and cataracts and other UV-related diseases would be skyrocketing, and we would have no idea why. And there would be this giant public health crisis, and on the news they would have all these experts saying, oh my God, why are so many people getting cataracts and skin cancer, melanoma, you know, and the death rates from melanoma are skyrocketing, and we wouldn't know why. But the fact is that didn't happen. And it didn't happen because a group of smart scientists doing basic science realized that a group of chemicals called CFCs, fluorinated fluorocarbons, had the potential to destroy the ozone layer that protects us from UV light. And they spoke up, and they explained it in public, and they went to politicians, and they went to the public, and the world acted, and we passed the Montreal Protocol on substances that deplete the ozone hole. So that's a great success story. And the thing that's even greater about it is that most people don't even know the names of those scientists, right? I mean, actually, if I asked this room, who could name one of the scientists who won the Nobel Prize for that work? Anybody know? We have any chemists in the audience? Yeah? Sherry Rowland, there we go. Okay, so we got one person in this room, Sherry Rowland, Mario Molina, and Paul Crutzen. They're very famous in science, but they're not exactly household names, right? But it wasn't just them also. I mean, they won the Nobel Prize, but there were lots of other people who worked on this. So there are all kinds of opportunities in science to do great work. So if you love science, if it's your passion, go out and do it. And yes, absolutely talk to people around you about it, because sometimes these things really, really matter. Now, in terms of the rest of the world, I don't think you have to be a missionary for science. I don't think you have to convince other people that they need to be scientists too. We need scientists, but we also need lawyers and activists and teachers and nurses and doctors and everything else. So I'm not one of these people who thinks that universities need to be having massive programs to encourage more people to go into the STEM fields. I actually don't believe that. I think we have enough scientists. What I think we don't have enough is of enough scientists who are willing and able to communicate their findings to the general public. So I would like to see the scientific community take on board a little bit more the responsibilities of communication. And I was part of a program when I was at UC San Diego where we actually got funds from the National Science Foundation to make communication part of our graduate program. And so our students would be more equipped to talk in public about why their work mattered. So I'd like to see the scientific community do more of that. And I think if we have the same number of scientists, but explaining what they do a little bit better, I think that will help a lot in the world.
Yeah, so this morning, Robert De Niro decided he would tell the world that, vaccines are really a problem. And the reason he withdrew the film from his film festival because all the other filmmakers decided they weren't going to come if he showed it. And so.
Weren't going to come if he did show
That's
the
right. If he
film.
showed it, the other filmmakers decided they didn't want to show up, so he canceled the film. But this morning on the news, he said that vaccines are there's definitely something there. And what I'm amazed as a scientist is I think the public doesn't have a really great understanding of how you get really famous in science, and that is to disrupt the current belief system. And all of those people you showed up there did that very famously. People thought the world existed one way until they came up with an alternative theory. And so can you talk about that a little bit and how the messy, sloppy side of science, where we have a lot of noise in our data, and that takes a long time to kind of get, becomes doubt in people's minds until there's so much convincing evidence that eventually the world kind of changes its views.
Yeah, thanks for that question. So I think there's two important things going on there. So the first thing is what you alluded to, that sometimes people will say, oh, there's a conspiracy in the climate community to suppress dissent. I don't believe in climate change and I'm being suppressed. And as you said, the reward system in science actually goes the other way. I mean, if it were the case that there were some compelling evidence to show that our understanding of the climate system was in some important way wrong or incomplete, any scientist who could demonstrate that would become wildly famous and would probably win a Nobel Prize and would certainly get elected to the Academy. There is huge reward in science for being able to show that all your colleagues got it wrong. So, and that is what Darwin did, and it is what Einstein did, and it is what Copernicus did. And all of the biggest names in the history of science are people who did that. So you're absolutely right about that. So I do think that's important for the public to understand. The idea that there's kind of a conspiracy to suppress dissent is just really not plausible, because the rewards for successful dissent are in fact so great. So that's one question. That's a question about the dynamic of what happens inside the scientific community. So if anybody had good evidence that vaccines caused autism, you could be sure that that evidence would be taken very seriously, not just in the scientific community, but also by the companies that manufacture those vaccines, because they would have to be very concerned about that. Although they might launch disinformation campaigns, which is another issue, of course. But the phenomenon of De Niro, I have to say, is heartbreaking to me. And this gets back to your question about what scientists need to do. One of the things that's upsetting to me when something like this happens is I'd like to see the head of CDC, any president of any college or university in this country who's a biologist or a physician by training, or an immunologist, or any field relevant to this question, needs to stand up in public and say absolutely unequivocally, in no uncertain terms, Robert De Niro is an unbelievable actor. And we have the most amazing love and respect for the work he has done as an actor. But he's not a scientist and he's not a physician. And he's doing damage. He's hurting people, because when people don't get the vaccines that their children need, people die. And when you don't get your children vaccinated, you don't just put your own family at risk, you put your neighbors at risk too. We talked about this earlier in the master class, right? These issues are very, very poignant and to some extent vexed, because it's not just a question of personal freedom. If I decided not to get vaccines because I didn't want vaccines, and the only person I was putting at risk were myself, I would say that in a free country and a democracy, it's my right to do something stupid, right? Like, I have a right to be an idiot, and I have a right to take chances, and it's up to me. And I do things that other people might think are dangerous. I'm a rock climber, I ski, some people think that's dangerous, but it's my choice, right? But when I do something that puts other people at risk, when I smoke a cigarette and exhale my secondhand smoke next to this young, beautiful young woman who wants to live a long life, then I'm doing something that's not all right. I'm doing something immoral, right? Because I'm putting her at risk, and she's not choosing to smoke. And that's why we did ban smoking in airplanes and restaurants, because the scientific evidence demonstrated beyond any reasonable doubt that secondhand smoke kills people. It kills flight attendants, it kills waiters and waitresses, it kills bartenders, and it kills your own children. So not vaccinating is like that. When you don't vaccinate your children, they can die. And when you don't vaccinate your children, their classmates in school can die. And we need to say that really clearly. And a lot of scientists don't like to talk in that language because it sounds very dramatic. Like, I'm talking about people dying. Sorry, I'm just picking something up off the floor. And a lot of scientists don't want to talk about people dying. They want to talk about the statistics, and that there's a 5-time greater chance of dying of lung cancer if you smoke, But that's not what moves people, right? So I think we need to be willing to speak clearly and directly. The power of drama, the power of film and television is the emotional response we get when we watch a powerful film or a television show. And I really learned this working with Robbie Kenner, the filmmaker with whom we made Merchants of Doubt. To make a film or a TV show, you have to do something that goes against everything you're trained as a scientist. As a scientist, you're trained, like the scientists in the front row are nodding, you're trained to be calm, you're trained to be dispassionate, you're trained to use statistics and charts and graphs, you're trained to stand behind that podium and not walk around the room and not make eye contact with nice young people. You're trained in a way that does everything possible to make you a bad communicator, right? But good communication is about making eye contact. It's about making that personal connection with people and getting people to think that you're trustworthy and to speak in language they understand and not to use terms that are jargony and confusing because that puts people off, but just to speak in plain language that people understand about life and death and health and sickness and protecting our children. So we don't do that. So De Niro gets up and he says, well, there's something there, right? And that's a classic doubt-mongering tactic, right? If I say, oh, there's something there, and you say, oh, no, there isn't, well, now we got to fight, right? And so now the audience thinks, oh, I don't know, there might be something there, and Robert De Niro, he's pretty famous. And I know who De Niro is. He's this incredibly famous guy, and who's this egghead from Harvard? I don't know who she is, right? So it's a real uphill struggle, but that's why scientists have to get involved. So I really hope that someone from the CDC says something about this, but I would say based on experience, the odds are less than 50-50 that they will. I mean, I can't tell you how many times in the last 10 or 15 years I've heard someone say some kind of nonsense, and I've thought, okay, for sure, someone from the CDC is going to say something about this, or for sure the president of the Academy is going to say something, or like, where's the president of the Institute of Medicine right now? Like, he should be on television saying, Robert De Niro, we love your films, but, please just keep making films, right? Right?
Quick question. It seems to me that this kind of conversation would be better served if we acknowledged that people don't make beliefs based on evidence, right? And I mean, almost none of us do, even the scientists among us.
Yeah.
I wonder if that's part of what you're getting at, right? Is that scientists present their point of view with graphs and charts and evidence and so forth, but that's not how it actually works, right? I mean,
Yeah, yes and no. I don't want to push that too far. I mean, it's become kind of a truism to say people don't make decisions based on evidence, even scientists. And I actually think that finding has been a bit overstated. What we know is that they don't make decisions only based on evidence, and we know that people are very influenced by who the messenger is, and that people are much more likely to believe a message that comes from someone who they consider a trusted messenger. But that's not to say that people are impervious to evidence either, because there are also studies that show that under the right circumstances, people do learn. And let's face it, we wouldn't have colleges and universities, and we wouldn't spend thousands of dollars and millions of dollars building universities if we didn't think that our students at least absorb some of what we told them in our classes, right? So I don't think it's right to say that people don't make decisions at all on evidence, but I think it's right to say it's not enough. Facts are not enough. You can't just throw facts at people or show them charts and graphs and think that will be sufficient. You have to think about how you can explain it in a way that makes sense to people. And that is hard because different things make sense to different people. And I mean, one of the things the advertising agency has known all along is know your message, right? I mean, I've had the opportunity to travel the United States giving a lot of talks. Sometimes I feel like a presidential candidate when I say this. But one of the most interesting things about traveling is listening to the radio or watching television in different places because the advertisements are different in Rhode Island than they are in Missouri or Oklahoma or Washington. And advertising are tailoring messages to different markets, right? People talk about market segmentation. But again, scientists don't do that. Scientists think, oh, here's my chart, here's my graph. It's universal, everybody will understand it. And that's not true. And that's hard for us, right? Because it means that we've got to work at thinking about, well, who are our audiences and how do we communicate in ways that make sense to them? And that's really difficult, especially because as a scientist, a lot of time you don't actually know who your audience is because you don't do market research and nobody's doing market research for you, right?
Last question.
I was just going to say, in the bipartisan culture that we have in our politics today, you can easily demean science by just chopping up to like liberal agenda. And what do you think that political figures that do support science and do support that stuff can do further to make their claims to a wider audience, so it's not just chopped up to fear mongering or, dogma?
Yeah, well, I think that's a very difficult question. And of course, I'm not a political scientist. I'm a scientist and a historian. But one thing I think, and there's some evidence from history to support this, there's some evidence from psychology, people are very sensitive to malfeasance. People know that there are bad actors in the world. And one of the questions I got a lot when I first started talking about the Merchants of Doubt work was people would say to me, well, given how powerful the tobacco industry was, and the tobacco industry owned senators. People used to joke about the senator from Winston-Salem, right? Given how powerful they were and how much of the economy of the Southeast United States depended on tobacco, how did we ever get tobacco use in this country under control? And that's a complicated and interesting question, and it isn't just one thing, but one of the things we do know from historical evidence, public opinion polls, and other data is that the legal prosecution of the tobacco industry played a very significant role. Because up until that time, a lot of Americans had thought, well, the tobacco industry is just selling a product that people want. And a lot of people say the same thing today about the oil and gas industry. But then we found out that, well, it wasn't that simple, that they were lying to us about what they knew about the harms of their product, that they were deliberately manipulating the nicotine levels in their products to make it more addictive, that they lied about the addictive qualities, that they bribed congressmen and senators, and that they broke the law, that they conspired to defraud the American people. And when that information came out, a whole generation of people, of whom I was one, came to realize that these were not just honest companies selling us a product that we wanted. These were actually criminals in expensive suits. And I don't use the word criminal lightly. They were convicted of conspiracy to commit fraud against the American people by the U.S. Department of Justice. And even today, the tobacco industry is facing criminal prosecution in Europe for money laundering involving terrorist organizations and illegal cigarette smuggling. So these people are criminals. The things they have been engaged in are unbelievable. And sometimes I do feel like I could get hysterical because when you spend time reading tobacco industry documents, you think, oh my God, like you can't believe the things you're reading. You can't believe it's true. And there were times I just felt so grateful I had a co-author on the Merchants of Doubt project, because I would call Eric Conway up and I would say, Eric, I want to read you this document. And I want you to tell me, am I overreacting or is this unbelievable? And he would say, no, you're underreacting. It's like, and we would say, how do these people sleep at night? So making it clear to the American people that this really was a criminal enterprise, that these people were venal, and that these people didn't really care who they killed, that was hugely important in shifting public opinion away from viewing cigarettes as a legitimate commercial activity to viewing it as problematic. Now, we didn't solve it entirely. These companies are all still in business, and one of the sad things about the tobacco story is that they took a lot of their business and exported it to the developing world, where smoking rates are skyrocketing in many countries. So we didn't entirely solve the problem, but we did make a lot of headway and save millions of lives here in the United States and in Europe as well by exposing these activities. So what does that mean for us today in respect to climate change? Well, as many of you know, 13 state attorneys are now investigating the fossil fuel industry for potentially illegal activities, and I think that's really important. I think we really have to confront the question of whether or not what they did was illegal, and I'm not a lawyer, so I'm not in a position to judge. That's for courts and juries to decide. But even if it turns out what they did was not formally illegal, I think we know from our work and other people's work that what they did was certainly immoral. And I think we have to be able to say that and say, to knowingly continue to sell these products and to knowingly continue to look for more of them, to continue to explore for more fields, reserves of oil, gas, and coal at this stage in history, knowing what that means for the future of people on this planet and the future of plants and animals and coral reefs and fish and all the rest, I think that's immoral. And I think we need to begin to say that so we can begin to think about moving away from fossil fuels as a problem that anyone who cares about the future of, and I don't like to say the future of the planet, because it's not about the planet, right? The Earth, the rocks on the Earth are going to be fine. It's about us. It's the future of life on Earth, and it's about our own health, well-being, and prosperity, or like we said in that final slide, so what if it's a hoax and we make a better world for nothing, right? This is about our future, and I think if we can begin to get that message across, that's not a Democratic or Republican or independent message. We all care about our future. We all care about our children. I mean, public opinions consistently show if one thing all Americans have in common, it's not that we all love apple pie. So we all care about our children. So I think that's a message that, to the extent that we can begin to get that across, maybe that will make a difference.
That is a great note to end on. Thank you very much. One final comment. Dr. Oreskes will be outside signing books. I saw there were a couple of hands. If you have a question for her, you should feel free to run up to her now or ask her a question outside. Thank you all for coming.